welcome back. We've got a do now. Do we still have do nows when we're at home? I guess we're going to have to. So our do now today is what is structure? And since I can't wait for you to raise your hand, I'm just going to have to tell you. Okay? Structure can mean a lot of different things. But when we're talking about a built object, the structure is how the parts or elements are combined and organized. The object is held together and it keeps its shape. So what does that mean? It means that when an object breaks, it has lost its structure. So we're going to be building model bridges, and we're going to have to design a structure for them. We're going to be organizing and combining and building all of those parts together to make a new shape. And then we're going to see how long it can hold together as a structure until it no longer can hold together and keep its shape. So that's going to be our goal for this first project. So the first thing that we're going to be talking about are stresses and forces. And a lot of these stresses and forces are going to be pretty familiar from lessons in the past. So some of these should be reviewed for us. And our first force is compression. So as you can see from those arrows pointing together, this is a crushing force. So when you squish something together. So if you want to get really technical, compression is when we are forcing the molecules to be closer together than they already were. So an example of that would be crushing a can of soda. The foundation of your house is under compression. Trash compactor on a garbage truck, its whole job is to compress that garbage and squeeze it into a smaller place. Now certain materials are really strong under compression and certain ones are not so great. So when I think of materials that are strong under compression, I think of masonry products. So things like stone, concrete, bricks. These are obviously the best choices if you want to hold up something that weighs a heavy amount. I've got this picture of a little arch bridge, and it's very similar to the little stone arch bridges that we have on our parkways here on Long Island. So like the Northern State and the Southern State and the Sunken Meadow, they all have these little arch bridges on them. So the way that they work is as traffic drives over the top, the weight is transferred from one block to the next block to the next block until it reaches the ground. Whenever you have a structure, the forces and the stresses that it's standing up to and the weight that it's holding up, it all needs to get down to the ground. So all of that force will go down through the foundation and back to the ground. Hi, here I am with my stone arch bridge. Very strong under compression. Just like we saw in the pictures, when we put weight on top of an arch, it will go from one block to the next block to the next block to the next block until it reaches down to the ground. So if I lean on this, it actually gets stronger as I push on it. But if I did the opposite and I pulled, it all just falls apart. And this shape actually holds itself together using compression. So you can see no fasteners, no glue, nothing needed, just goes right, back together. See, no tricks. All right, our next force is the opposite. It is tension. This is a pulling force. So we're stretching out the molecules and making them move further and further away. So a good example of objects that are feeling tension could be the chain on a swing set, the string on a string instrument like a guitar, or even like the support cables on a tent or a tower. Okay, so I've got a shape that's really strong under tension, a rope. If I pull on it, it holds its shape really well. If I push on it, it doesn't really do anything. It just flops away. So certain materials that are strong under tension could be nylon, like this rope, or it could be steel, like you would use for a chain or a wire. All right, so here is the question. Can an object experience both compression and tension at the same time? Can it feel a pushing and pulling force at the same time? And the answer is it can. And it can in a couple different ways. So if an object is being bent, so let's imagine this bench right here is the dugout and for our baseball team or our softball team, and it's the change of the innings, and everybody's coming off the field and they sit down on the bench, and it will sag and bend underneath the weight of all of our athletes sitting on the bench. So the top of the bench is feeling compression, and the bottom of the bench is feeling tension as it bends. All right, so let me illustrate how a bending beam feels both tension and compression at the same time. So we looked at that picture of a bench, and I have a beam right here with parallel lines drawn across the whole thing. So I'm going to bend it just like the picture, and as you can see at the very top, those lines move closer together. So they're being compressed. And at the very bottom, those lines are moving further apart, and it shows that the material is feeling tension. Okay? So let me move that a little closer, and if I do the opposite, it feels the opposite. At the top, it's feeling tension. At the bottom, it's feeling compression. And when I put it back, it's even all the way across again. Another way an object can feel compression and tension at the same time is in different parts of the same object. So this drawing right here shows a cable stay bridge. So the tower is always under compression, and the cars driving over the road are pulling those cables, and they're always going to be under tension. A suspension bridge would be exactly the same thing. The anchorages, that's where the cables are attached to. They're going to be pulled. The cables are going to feel tension. They're draped over the towers. They're going to push all the weight from the roadway down onto those towers. And those towers are going to be squeezed between the weight of all of the traffic and the earth. So they're going to be under compression. Our next force is torsion. So you can see a big arrow going around in a circle because torsion is a torque or a twisting force. So a good example would be cars spinning their wheels. There's a lot of torque, a lot of torsion. Don't do that when you get your license, though. Don't do that. You'll lose it right away. A better example would be something simple, like you just turning a doorknob. So that twisting motion that your wrist makes when you turn a doorknob or you twist a screwdriver, those would all be examples of torsion. So I always hear this in reference to a car's ability to turn its wheels or your ability to turn a wrench or a screwdriver. That's usually where I hear the term torsion. Now our next force here is shearing. So shearing is a cutting force. So you can see those pictures. I've got metal shears, I've got fabric shears, I've got head shears. A lot of times when you've got specialty scissors, they're called something shears. So the definition of this force makes portions of an object move in parallel. So the best example is when you cut something with a scissor. Here's, I've got my shears, and you can see that the blades slide past each other in a parallel motion. So that goes along with our definition. So when I want you to think about something shearing, I want you to think about it sliding past, just like a scissors blade slide past. Things that are susceptible to shear are often connection points. So bolts, screws, welds, different ways of connecting two objects together. If those two objects slip past each other, they'll cut or shear their fasteners off. So, what's another name for a scissor is a shear. That's where they get it from. All right, and our final force before we move on to our stresses would be racking. So racking is a force that distorts a square or a rectangle and causes it to become a parallelogram. Now this is probably a new one because it doesn't happen in nature. You guys first learned about these forces and stresses when you did like tectonic plate movements in 6th grade, and we might have talked about them a little bit if you did the House of Cards with me in MST as well. But it doesn't occur in nature because to have a square or a rectangle, you need equal opposite sides and 90-degree corners. But when something becomes a parallelogram, it no longer has those 90-degree corners. Now this often affects things like connection points. So you can see in this picture is right after an earthquake happened. It shook the whole structure and it broke the connection points, and it's a lot easier to break the connections than the materials in some cases. So the way that the walls and the floor and the ceiling were all connected broke before the actual wall, the floor, or the ceiling. And it caused the whole building to kind of tip over instead of crumble or break apart. All right, here I've got my square. Now, all squares are parallelograms, but not all parallelograms are squares. Now, squares and rectangles both have equal opposite sides, just like all other parallelograms, but they also have to have 90-degree corners, and that's what makes them special. Now, in an earthquake, if this was going and shaking all over the place, it's easier to distort the shape than it would be for me to break the beams. So they could just basically tip over instead of cracking and breaking apart. And that's where you see the racking force most often. All right, so now I want to talk about stresses. So forces describe the feeling that an object is under, and the stress is describing what is internally happening to that structure. So we've got kind of like a cause and effect, right? So the stress is the cause, and the force, those are the things that we just talked about, that would be like the effect. That's what it's feeling. So the first example we've got here is the Tacoma Narrows Bridge. Now you could look at these pictures and you can see something pretty wild is happening. So in the two top pictures, the bridge is together. You can see it looks like it's twisting. It's actually swaying and moving back and forth in the wind, and we're going to look at a little video of this happening at the end. And then at the bottom, you can see the whole thing has fallen apart. So we're going to take a look at how that happened, but first we need to talk about how a structure feels stress. So the first type of stress is what we call a live load. Live loads are stresses that change or are dynamic. So good examples could be weather, vibrations, traffic. Those would all be things that can change. So if you look at the picture at the top, we've got all those red arrows. Those would be your live loads. So precipitation landing on the roof of that house, the people and the furniture that move around on the inside, and then the wind blowing against the wall. Those are all live loads. Now the blue arrow represents the weight of the structure itself, or gravity, and that would be something different. We would call that a dead load. So this is the opposite. It's a stress that does not change, or it is static. So it can't change. It always stays the same. There's no change in the weight of the structure. There's no change in gravity. We don't have like heavy or light gravity days. It's always the same. So if you look at the picture above, it shows the same thing, but in an office building instead of a house. The dead loads would be the building materials like the concrete, the steel, and the glass. And the live loads would be like the people, the furniture, and the materials that can all move around. Now the furniture in your house or the furniture in the classroom or a building, it might stay in one place for a long time, but it can move. So we would consider those live loads, even if they don't move very often. And the critical load. So this one's going to be really important to us for our project. So after the critical load is applied to a structure, it will cause it to fail. Now, when I say a structure has failed, I don't mean like it received an F on its report card. Think about that definition we learned at the beginning. So when a structure fails, it no longer holds together and it no longer keeps its shape. So the critical load is what we're trying to determine on the bridges that we're going to be building. The higher we make the critical load, the stronger we would say that bridge is. Now our final term here is deflection. This is the distance a structural element bends under a load. So it's a measurement of change. I always like to think of a diving board because I feel like it's really easy to look at. I think everybody's seen somebody jump on a diving board. So when nobody's standing on it and it's just sticking out into space, that would be like 0, no change. But when a diver jumps on the end of the board, it's going to deflect or bend underneath their weight, or the force of them jumping against it. And the distance that it changes is the deflection. So when something changes, whether it can rebound or not, like if it's a springy surface like a diving board or like a bridge where it might change when there's lots of traffic on it and then rebound to its normal spot after. Deflection is that measurement of change. Now let's take a look at the Tacoma Narrows bridge disaster. So the Tacoma Narrows Bridge was built in the 40s. The film is from then as well. It is not like a normal news report because people used to get their news at the movie theater. So because it was delivered in the movie theater, it's got kind of a different look to it. All right? So let's start it out and check out the film.
Dawn of a fatal day, and the wind begins to speak with a roar that no man can fail to hear. In a 40-mile gale, the center strand weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you could see it as you do now. There's an automobile come on the heaving roadway. The 11,000-ton center span trips and strains the giant cables that support it. Cables of 6,300 wire strands, each 17 inches thick. Back out of the danger zone, all stricken spectators are driven to safety as the bridge gyrates like a nightmare high above the river, twisting, turning, curling. The lone motorist is forced to abandon the car. He has but a few minutes in which to save himself. Face to face with fate, his destiny hanging in the balance. Will he heed the last warning or perish with the doomed structure? But he saves himself by seconds. No structure of steel and concrete can stand such a strain. Steel girders buckle and giant cables snap like puny threads. There it goes! Divided as to the cause of the disaster. Some claim it was the use of solid girders, others differ. But whatever the reason, Tacoma will rebuild. This time a bridge that will not provide a super thrill in the news.
All right, I'm going to stop it right there, but I'm going to slide this back just a tiny bit so we can take a look at the picture. All right, so I don't know if you guys all caught the explanation, but at the very end, the announcer said, engineers are divided, but many think it was the solid steel girders. So the sides of the bridge were the solid steel girders. And this is the area where the wind caught the bridge. So the wind was the stress, and the torsion, that twisting that you saw, that was the force. So that was kind of the cause and effect that caused this bridge to break. All right, we're going to pick it up next time with different types of bridges. Bye-bye for now.